Okay, assalamu alaikum and good morning. I think we already covered CPU scheduling and the simulations of it. I have given 2 sessions for simulations. However, the last few slides in the lecture notes give you additional information about how to extend the simulation program to shortest job first, priority scheduling, as well as round robin. Okay, and I think there is a hint that I have given also on how to write the simulations for preemptive shortest job first as well as preemptive priority scheduling. Okay, your homework will basically be what? Have you seen the homework, second homework? Okay, so it's about the preemptive priority, right? Okay, preemptive priority, and you're supposed to find well, lots of performance measurements and format the output nicely in a file, okay? So we're gonna conduct a session, but it's out of the class session, okay, to help you doing this kind of homework, any discussions, any questions that you have, and maybe sometimes we can have, brainstorming together, okay? Different than the office hour will be much better, okay? I mean, in case you needed the office hour for something else. If we cannot find that, then we can do it in the office hour, okay, during the office hour time. Can you please arrange for that, a time that's suitable for you on Monday or Wednesday? Okay? Yep? Okay, and let me know about it, please. Otherwise, if it's after 2 o'clock or 1. Okay, check that. No problem. Okay. Otherwise, Thursday, late. Okay, I mean afternoon. Okay. So today we're going to talk about multithreading. Okay. 1 hour is quite okay. I don't mind. I mean, we can extend more than that. 1 hour, 2 hour, 3 hour. As long as I'm free, you're free. It's fine for me. Okay. The problem is scheduling the time and the place. Otherwise, I don't mind to sit with you even 4 hours. It's fine with me. Okay. So today we're going to talk about multithreading. Okay. So we're going to introduce the concepts of multithreading, and then we need to compare thread to process. So basically, what's the difference between a thread and a process? Okay. Why multithreading is important? What are the advantages of multithreading? And then we will look at the support of multi-threaded programming or coding, okay? We also introduce the models of multi-threading related to operating systems, and then we move to examples of multi-threading with different ways, okay? One way is to use the C with Linux or Unix-based systems, and in that case, we're going to cover POSIX threads. POSIX threads. So we'll show you the concepts of POSIX threads, the main functions there that you can use to create threads, and we demonstrate some examples for you as well. Then we introduce Java multithreading, and this is going to be the first time we will get into Java, okay? So you need to revise, okay, information about Java, because later on we're going to use it heavily in synchronization. Okay. What's a thread? No idea, right? It's the first time you hear this term, okay? Okay. Consider a web page, okay? I mean, all of us really browse the internet most of the time, isn't it? And when you visit a page, you'll find that it contains multiple type of media, right? So you can find an image that's downloading halfway through, a video progressing in downloading and you viewing it, right? And maybe background audio that's running, a text displaying, a banner changing, okay? And things like that. So you have multiple type of media, and they are all progressing simultaneously, okay? But it's one application. And if you go view processes, okay, in your, for example, Windows system or even in Linux by using PS, you will find that there is a process that corresponds to the browser, right? This is a proof that this browser is what? The browser application is what? A process, right? However, it does things at the almost same time. Different tasks done almost at the same time. You are downloading something, okay, while you are viewing, okay? You are opening multiple windows and you're doing multiple things in it, okay? And all progressing, okay? So these tasks progressing simultaneously, we call them what? Threads. We call them threads. And all of them, they do correspond to the same process, to the same process. You view the processes, you will find only one, right? So that kind of process. And the same thing for the word processor as well, okay? You'll be typing, okay? At the same time, there is another sub-process. I won't call it sub-process, but I'll call it a thread, a task, okay? That does something else. For example, keeps track of what have you been doing in terms of editing, okay? And this is the beauty of what word editors, right? You can undo, right? The best thing, right? So basically, there's another type of tasks that are running simultaneously in different type of applications. Similarly, the web server. A server that hosts an application, okay? And multiple users are accessing the same application simultaneously. However, it's one application, one process at the server, right? Multiple clients, who are the users, are accessing that application, and they all progress simultaneously. So we say that the service is offered to be as what? As multi-threaded service, okay? Multiple threads. Each thread will deal with one particular client or one particular user. We will discuss this in details, okay, when we talk about client server or network programming. We're gonna implement a multi-threaded server, okay, that you can connect to it with network programming, I mean sockets in this case. So a thread, now I can have a definition for it, okay? A thread comprises a thread ID, program counter, register set. We need that. We need a program counter because this is a task, okay, that will progress, and it can be what? Interrupted, okay? And then it needs to progress where, from the time it was stopped, right? I mean, at the point that it was stopped, okay? And so on. It also does things, so we need a stack, okay, to keep information of what had been evaluated or executed so far. It has a data section and so on. Now, it also shares. Now, we can have multiple threads within a process. The process itself, it has its own code. It has its own data, okay? It has its own OS resources that are allocated to it, including open files and so. It has its own scheduling information, okay? But also, it has multiple tasks. Each is represented by a thread, where the thread has the information shown here in red, okay? Now, all of these threads, they run within the process, which means all of them share what the process has. All of them share what the process has. So all of these threads, they run in the virtual memory, okay? They have the same virtual memory of the process, okay? So they can access that, okay? They can access that virtual memory. However, okay, each of them is independent from the other, okay? So this is a concept, the concept of threads. What's so important about threads? Well, the very first thing is responsiveness. Responsiveness in a way that you are working with a process and you're doing multiple tasks, okay? So you will find that they are progressing simultaneously. You don't have to wait for one task until it's finished and then you can start the other one, right? So the response of the system is much higher, okay? If it did not respond here the way that you want it to respond somewhere, okay, maybe the way you want it or even better, right? Or at least you can have multiple things done at the same time. The other benefit is resource sharing, since we have agreed that these threads, okay, they share what the process has, okay? And all of these threads, they live within the same process. This is not true for processes. If I have multiple processes, by default, they don't share anything. If I want them to share something, then I have to use some kind of inter-process communications, right? A pipe, a file, shared memory, or anything, different mechanism. They are economical in multiple things, okay? One of it is that their representation, okay, is much smaller than the representation of a process. Okay, because it has less things than what the process has. Okay, so the task underscore struct in Linux, it is actually used to represent a process as well as the thread. But however, the kind of information that's saved in there, okay, for a thread, much less than that of the process. Okay, multiple threads, okay, they could have only pointers to what the process has in terms of information. Okay, that's the reason why in Linux we call it task underscore struct. We did not call it process, neither thread, okay, because it's the same presentation for all in terms of the data structure that's used for the OS, Linux, right? Linux OS. On the other hand, since these threads, they do run, they are like within a process, okay, and we know so far, okay, we have seen that most of the operating systems, they are multitasking, right? Multitasking in the sense that processes, they share the resources of the system. They share the CPU, right? So each process will be executing for a certain amount of time, correct? And then there is a context switch, right? Context switch, and for that, the CPU will be dealing with another process, okay? So each process is given a time slice in a way or another to execute, isn't it? Now, within the time slice of the process, then we can have multiple thread switching. So these threads, when they are executed within the time slice of the process. Okay. Now, when I do context switching for a process, okay, that involves system calls. Involves what? System calls, and system call is expensive. Okay, in terms of time, in terms of interrupting to the kernel, okay, to do a particular task, which is basically keeping information of the process currently executing, and then what? Taking another process in, calling the scheduler, and all that kind of stuff, right? However, the context switching of the thread is much lighter. And it is done, okay, within threads, within the same process, okay? This can be done within, using supported runtime libraries for thread scheduling, Okay, so we can, one of the examples says that the solar is, okay, the creation of a process is about 30 times slower than the creation of a thread. Okay, because the amount of information that we need and the resources that we need to allocate to the process. As well as the context switching is about 5 times slower than what? Than the thread. The thread is much faster. The last point is scalability. Well, if I write a code, okay, to execute multiple tasks, and I just wrote it with a normal, okay, way of coding, which is sequential code, okay. Then if I run it on a system that has one single CPU, it executes as expected. A process, then another process, they will take time slice, okay. And if I execute this code, which is multiple tasks implemented as multiple processes, then if I run it on a multiple processor system, okay, where I have multiple processors, again, it will execute what? On one CPU. It will execute on what? In one CPU. The utilization, okay, will not be really as good as that of threads, okay? If I wanted to execute on multiple CPUs and grant that these multiple processors execute on multiple CPUs, then I have to do something additional, okay? Additional. As well as I have to handle what? The inter-process communications among these processes, okay? While if you wrote a multi-threading program, okay, naturally, when you execute it, okay, it will utilize what? The multiple CPUs that you have in your system, okay? So we can have logical parallel, okay, programming using multi-threading, okay, that will run on physical parallel systems, okay? This is a summary of what I have been talking regarding threads and processes. So this is a comparison, full comparison. I thought it would be useful. So we have, in terms of representation, I'm comparing processes to threads. Processes heavier, threads lighter, context switching faster in threads, okay? and it does not involve any system calls or invoking the kernel in the context switching itself. The mechanisms to perform the context switching system calls by here, what? Runtime libraries, okay? The responsiveness of the system, the overall system, is faster with multi-threading because we've seen that they're processing simultaneously. Memory requirement, lighter, okay? And in terms of the existing environment, the process can exist by itself. However, threads, they exist within a process, Okay, and for sharing resources, naturally sharing resources of the process while they are with inter-process communications. For utilizing of the multiprocessor system, this does utilize that, while the one not by default, okay? Concurrency here, do I need to have or to consider concurrency issues when I implement multi-threaded programs? I must consider that. Just to recall that, concurrency, okay, needed to be considered because we need to coordinate the execution of multiple threads sharing data. They do share, right? And when they share data, we have to coordinate how do they share the data. The reason to do so is what? To maintain consistent view of the data, right? So here we need to consider lots of what? Concurrency or synchronization. That's why we're going to have 2 weeks talking about synchronization. And then in terms of speed of creation, this is faster. Speed of execution is faster, as well as in terms of economy, okay, overall, okay, you will have the thread much cheaper. So when do I need really to have multiple things done simultaneously, not in a sequence, in parallel? When? In real life. Always, right? Always. Didn't you notice yourself been doing multiple things at the same time? Okay, right? Multiple things done always at the same time. We're doing something in here, and then maybe you started something, okay? Instead of waiting for it to do something else, okay, and then so on, okay? So all of us do this thing, okay? Multiple things at the same time, okay? If you want to have an example of that, just watch your mother cooking. Okay, and then that's the best example to see how can she naturally, okay, manage, okay, concurrency, okay, and time it even, right, to do things perfectly, the least time needed to achieve that delicious food, right? Okay, and so there are challenges, okay, of implementing such thing. Most of the softwares nowadays, they do not really utilize, okay, the multi-threading, okay, implementation. They do not really utilize in the code itself, okay, the existence of multiple processors on almost in every computer system nowadays, right? Your personal computer, your laptop, okay, multiple processor, multi-cores, multi-threaded cores, call them, right? Hyper-thread, right? But the code itself of the application is not written, okay, to utilize that perfectly. Instead, programmers, they keep writing the same sequential way, their application, and they will say, it's okay, those who, the vendors of the hardware, okay, they have, together with the operating system vendors, okay, they have implemented, okay, implicit way of utilizing the hardware, So they They are dependent on others, okay, of running their sequential code, okay? Why they don't even write it, okay, in parallel to have full utilization of the currently existing parallel environment? Because of many difficulties, okay? Well, the first thing is lack of expertise in doing something like this, okay? And so we need to know some of the challenges, okay, that people facing when they write this kind of applications, okay? One of it is dividing the activities, to know what activities can run in parallel, okay? And so this involves sometimes timed activities and sometimes no event-based, okay, parallel activities. So you'll say that I can have run these two activities in parallel. However, the third one can't run in parallel, okay? Okay, I can say that the running of activity C depends on the result of activity B. Okay, so for that, I can't run it, okay, in parallel, okay, and so on. So we need to find dependencies between activities, and based on that, design or model, okay, what can be run in parallel. This is the most important thing, by the way, right? Secondly, we need to balance, okay? We need to balance to ensure that the task contributes as much value. For example, if I can run two things in parallel, okay, but at the end, okay, I don't see much of a benefit of doing so, okay, then I might choose not to run it in parallel, okay? But someone might ask a question, okay, how come two things in parallel, okay, is not better, okay, is not better than running them sequentially? Okay. Well, when you run things in parallel, you need also, for starting, okay, to start doing so, okay, you need some kind of overhead or delay, okay? Plus, you need the effort of modeling and coding that kind of activity. And if the time difference is not really that much, okay, you can neglect it, okay, and not to do it and focus on some other activities that can really run in parallel. So the contribution should be really, okay, acceptable contribution for the parallel task that you have written. One important thing also is data dependency, okay? How data depend on the other data executed by multiple activities that are running in parallel, okay? Will one activity change the data that is shared by another one, okay? Or if I have data and I want to run the same process, however, multiple copies of it on the data itself, then in this case I have to partition the data. Okay, I have to partition the data, but multiple copies of the process will run on that data. An example of that is sorting. If you're given a list, okay, to sort, right, then we can divide this list into two halves and then get two people to do the sorting. Okay, one will take care of half of the list, and then we merge. Merging is much easier, right? Okay, so imagine if you have like 10 people to work on one list. So this is data partitioning. Okay, data partitioning, the same task repeated. And the other thing is to test and debug, okay, such programs. So to do so, you have to understand how threads really execute, how they share data, what data they share, what data they don't share, and so on, okay? So this is under, well, concurrency programming. Concurrency programming is one whole topic. Most of the time is offered as a separate course, concurrency programming. It is very useful because once you do it, you can do parallel programming. Okay, so we have logically, in fact, you can code your own multi-threaded application by assigning a task to a thread, and these tasks will run in parallel within the time that's given to the process, the time slice. Okay, this is at the application level. However, later on, whatever thread you create at the application level has to be mapped to a kernel thread, thread, which is the actual execution unit, okay, in the operating system, an execution unit, okay? So that kind of mapping differs, okay? Some systems, they map multiple user threads into one kernel thread. Multiple user threads in one kernel thread. Others, they have each user thread to one kernel thread. So whatever you do, okay, at the user or application level, actually is what is reflected in the kernel, okay? And others, they do, well, a mix of this and that, a mix of this and that. So they can map one-to-one or what? Many-to-many. Many-to-many, but when I do many-to-many, of course, the number of threads at the user level has to be what? More than the number of threads at the kernel level, right? Now, if we're gonna compare these different ways of mapping, okay, between user-level threads, application-level threads, and the actual execution thread at the kernel, then in terms of management, okay, the very first one has to be managed by a library at the user level. Library at the user level. You have to be aware that these multiple threads, okay, they will be actually executing within one kernel thread. While this one, okay, one-to-one, you don't have to do any kind of management, okay, because one-to-one mapping. And for the third one, Well, you have to do user management in here, but you don't have to do it when the one-to-one is applied. As for blocking, okay, if you have multiple user-level threads within one execution unit of a kernel thread, and if one of these threads, okay, is blocked, that will result or will affect the rest of the threads within that kernel thread. So the blocking of one, okay, will block the entire process that has the multiple user threads. However, in this case, no, because each thread has its own what? Kernel. As well as in here, okay, because most of the time, well, we have a process, some of the, okay, the user level threads are mapped to, okay, together to one kernel thread, but others are also what? One-to-one. So if the one block, other threads also can proceed, who are mapped one-to-one, okay? In terms of concurrency degree, okay, there you have multiple simultaneous threads, but they map to one towards the end of the kernel. So you don't have really much of a concurrency, okay? And in this case, very high concurrency, as well as in here, however, this is higher, right? The highest, okay? In terms of running in parallel, okay, don't run in parallel multiprocessor, okay, because that's how they've been mapped, multiple to one, okay? Here, yes, they will run, okay, but the degree of parallelism is less than here, okay? Here, full utilization. Okay, in terms of the drawbacks that we've seen, well, now you can, from here, you conclude some drawbacks. Blocking, okay, no concurrency, and does not run in parallel, the three. Okay, so I'm trying to put just two sheets, this one and the one before, okay, to summarize the whole thing, okay, in terms of, in case you needed to study, okay, that. And here, we have one problem, okay? The problem is that whatever you create thread at the user level is mapped to a kernel level. So is there a limit? Okay. Usually in the kernel, there is a fixed number of threads that can run, okay, concurrently. Okay, so there is a max limit, a maximum limit. So a solution to this, okay, is by having a thread pool. Okay, thread pool. So for each process, there will be a thread pool for each process. And then the thread will be taking what? The process will be taking or will be assigned the threads out from this thread pool, okay? So assume that it's 10 threads there in the pool and the process will be utilizing all of it and wants to create thread number 11. Can't do that until one of the threads, the very first 10 threads created, until it's what? Terminated, okay? And then can reuse, okay, that kernel thread for it. Well, these are some of the examples of the systems, and you can see that actually Linux, Windows, they are what? Here. So that's a motivation to threading. Okay, so maybe you can relax a little bit of coding. You've been doing lots of coding in most of the classes before, right? But be aware that from next class, you'll be doing really lots of coding with threads as well. Okay, but it's interesting, yeah? So now, at the user level, okay, we want to code with multi-threading. How can we do that? Okay, that can be done by using libraries supporting this kind of coding. Okay, so we have three different libraries, mainly the common ones, okay? The POSIX threads library, POSIX threads library, which is sometimes we refer to it as pthreads, okay? In fact, we refer to it as pthreads because it's the POSIX threads library. At the same time, because every function in this library starts with pthread and then underscore. All the functions, okay, start that way. And then another library is the Win32 threading library, okay? Win32 threading library if you want to do multi-threading with what? With Windows operating systems, okay? And we also have Java threads. which is basically what we call it architecture neutral, right? Because it works with every architecture. So it is platform independent. Okay. So we're going to cover POSIX threads and what? Java threads as well in terms of what? Implementation. What does it mean to have runtime library that supports multi-threaded programming? Okay. It means that I should have an API there. You know what's an API, right? Okay. An API basically application programmer interface, right? That will tell me these are the functions available, the signatures, their arguments, the options, their return values, okay? And what are they used for? Correct? Plus, it has also some additional information related to the thread scheduling. Thread scheduling and the representation of the thread as well. Okay? So all of that is actually managed by the library. So you can see these are the things. Now, these libraries, they are implemented, okay, at the user level, or what? They can implement it as a kernel level libraries, supported directly by the operating system. So two different ways of what? Implementing these libraries. POSIX threads. Maybe we can leave the class with one example at least of how to create a thread, okay? So now we look at the library, which is the POSIX threading library, okay? pthreads. Pthreads has functions. Well, this library should provide us with an API, okay, to code with multithreading. These are the most common, okay, functions that are used for multithreaded programming. The very important one for me is the function to create the thread, right? Which is pthread underscore create. And you can notice that all of them, they start with pthread underscore, right? So pthread underscore create is a function to create a thread. I can also cancel or terminate the thread by using what? Pthread underscore cancel. I can deattach the resources, which means release the resources that were allocated to a thread by calling detach or deattach. Okay? I can test whether two threads IDs are the same, equal, okay, by using the equal. I can exit the thread. But we already have a function exit, right? We use it with the process. If you use the exit function, the normal exit function, or the underscore exit with small e, or the underscore exit with capital E, okay, it will terminate what? And what's inside the process? Threads, which means it also terminates the threads. Okay? However, okay, pthread underscore exit, it terminates what? The thread only. Okay? And the other threads will keep running. Okay, question. If I have written a C program and in the main function of it, I created 3 threads. Okay? I want the program after it starts, after creating the threads, I want the program to exit. To exit the main program, which is my process, right? I want it to exit, but I don't want the threads to exit. What should I do? The main program that created 3 threads, I want it to exit. But at the same time, I don't want the threads to be terminated. The process itself, the main, okay, itself is a thread. It's the main thread. It's the main thread, okay? So I can even call this, okay, pthread exit, I can call it in the main. And that will terminate the main. However, the threads are there, okay? It will terminate the main thread of the process. The process is still there, right? But however, what? The threads that are created are still there. Now, I can also send the signal, okay? If I want to send the signal from one process to another process, I use the kill, right? And now from one thread, from within the thread I want to send the signal, then I use what? pthread kill, which has the same signature as the kill that you have seen before. I can let a thread to wait for another thread. Remember when we talked about the difficulties of concurrency, I have to know, okay, which tasks have to be in parallel, and if one task depends on the output of the other, then I have to make it wait for it, and then it starts, right? So how can I do that? Well, in processes I can use wait PID, right? Here I use what? pthread join. Pthread join. So if a thread join another thread, it means it is waiting for it to terminate, okay? And self, if I want to get the ID of the process, I use what? Get PID, right? Get PID. But if I want to get the ID of the thread, if I call get PID from within the thread, what should I get? The process ID, okay? If I have 3 threads calling get PID, they will get the same thing, which is the process ID. However, if I call pthread self, it will give me what? The ID of the thread. See, these are some of the functions. Now let's go through this simple example, okay? And well, at the very beginning, the very first example that you see with threads, you might see that the signature of the function, which is pthread underscore create, is a little bit complicated. But in fact, it's not. And then later on, when you deal with it, well, more deeper or kind of coding, you will find, yes, it is. But now for whatever, okay, for this intro to be a thread, okay, all we want is to create a thread. To create a thread, it's a task within a process, right? So the way to implement it is by putting a function, okay? However, when I run this function, I want it to run as a thread, okay? So the code of the thread, which is what should be done by the task, is inside the function, inside a function. So that's what I do first. This is my function, okay? The function, it is a thread function. It takes arguments and it does something, function. If you notice that, it only receives one argument. And this is the signature always. It receives one argument. You can't set more, multiple arguments here. It receives one. But most of the time, functions, we send to it multiple arguments, right? We are allowed. So how can we overcome this problem? I will show you in a while how. And what's the argument type? Void to pointer to void, right? Pointer to void is a generic type, which means can be anything. So you can send any type, okay? And the same thing in here as for the return value of the function. Now, what should be in here? Inside the function, the thread function, anything you want. Any code you want, you can put it in here. This is the code of this task. Now, how to create this thread? I can use pthread create. I'm not checking errors in here, okay? But most of the thread functions, they do return what? 0, okay? If they are successful, and any other number if they are not successful, usually negative number, right? So here, pthread underscore create is the function to create the thread. So what do you think this function should take? At minimal, the name of the function which has the code of the thread, right? To know what to execute. So that's what we have in here, which is the third argument. The third argument. So what's the third argument? The name of the function which has what the thread should do, okay? The last argument, the last one, is what you want to send to this function. And if you look here, the function receives one argument. One argument. In this case, I don't want to send anything to the function. So this can be null or anything of type what? Pointer to void. Okay? So if it's not type pointer to void, anything else, but I cast here pointer to void. Between brackets, I write what? Void pointer. and then you put whatever you want. The very first argument is what? Usually when the process creates a thread, wants to know what's the ID of the thread, right? That had been created. So the ID of the thread that's created will be saved in the first argument. That's why I have defined it here, okay? Of type bthread_t. Clear? So now we are left with one argument, which is the second. The second argument corresponds to the attributes, okay? To the attributes of the thread, okay? Which we're gonna leave it null. We're gonna leave it null, okay? However, you can look at it, and these attributes, they correspond to, for example, scheduling information and other type of stuff, okay? Okay, so now I'm creating the thread. When I do this, when this is executed successfully, then a thread is created and it will execute. The difference, and then after that, what do I have here? Sleep. Because now I have two threads. This main thread and that, and they are executing simultaneously. If I want that to be done, okay, I can have a sleep in here, okay, for a while, okay, just for it to start, but not necessarily really need to have to sleep, okay, just to demonstrate to you, okay, they will run concurrently. And then here to print that I'm the hosting process, and this is my PID. And here, exit 0. You know why I put the sleep there? Why? If I did not put the sleep and I leave it exit 0, so I will have two threads, right? Assuming that this thread executed first, it will reach exit 0. And if exit 0 is reached, the thread that was created will be terminated. It will not execute. Okay? However, if I want to overcome this problem, what can I do? Remove this. And here put what? pthread_exit. Okay? Clear? Now, if I want to compile this with the GCC compiler or CC compiler, I need to add one more thing, okay, which is pthreads. So I can write, if the name of this like pt1, okay, and it is pt1.c, okay, then I write GCC pthread. So this is switch, right? Okay, GCC pthread, okay, then pt1.c, and then the -o, and then the output file. Clear? Okay. Now let me show you this. I have already, posted in the Blackboard most of the programs, okay, put in a zipped folder, as well as the Java ones, okay. Okay, let me go here. Okay, so now I'm in, well, okay, let me write this, GCC, and we said what? pthread is my switch, okay? And then what? I call it pthread1.c, okay? Say the output I want it in pt1. Now I just execute it normally, okay, pt1. So choose what? I am the thread of process BID. It's called the BID, get BID within the thread. And then I am the hosting process, right? They execute together. The important thing for you to remember here is that this is the last slide, okay? I'll look at it. The difference between a function and a thread. Because you have seen it, the thread is a function. Okay, but what's the difference? Okay, the difference is this. For functions, okay, when a process calls the function, right, then The execution goes to the function, right? So now whatever the function has in terms of code will be executed, and the process will stop there, right? Waiting for the function to return. For the function to return, because the functions return. Not necessarily to return something, but they would return, right? They will return. And only then the process continues. While here in multi-threading, after the pthread underscore create, after you create the thread, okay, the thread will progress and the process will progress. Plus, the thread does not return. The thread does not return back to the process. Okay? While here, it does. Okay? Progressing simultaneously. It's very important. So that's the difference between functions and threads. In case you've seen it, well, it is a function. Well, it's not. Okay? Next time we continue talking about pthreads and Java threads as well.